Now this is on 50 volts for division. I'll bring this down to the line. And we're putting in about 80 volts now that it's showing there. This line here is hooked across a 002 shunt, and I'm set on 20 millivolts per division, and so that is indicating the amperage that's going into the motor. Now we'll turn this over here a little bit. Now you can see the little pulses I'm putting in. Very small amount of amperage I'm putting in. I'm getting as much back. We'll put this on 0. Get it as accurate as possible for the perfectionist. Now, these pulses that are going in are very short in duration. These back EMF pulses down here are wider, actually, than the forward EMF pulses. Everything below the line, I'm capturing in these condensers here to use in the next pulse, so that I don't need to take quite so much electricity out of the battery. Now, this motor is equally as good a generator as it is a motor. Now, I'm going to shut the power off going in. And you'll notice a sine wave, but the sine wave, as it slows down, collapses. And we're just hooked on to one phase of the three-phase. I have here a three-phase bridge rectifier that's taking and snubbing the motor. Actually, if I take that off, I'll have 1,000 more RPM, and I'll have real long down here. But that runs the risk of burning out my transistors, so I keep it snubbed down a little bit. Find a quiet speed so we can talk. But I designed this basically for electric cars because of the torque. The torque is unlimited. Find a quiet speed so we can talk. But I designed this basically for electric cars because of the torque. The torque is unlimited. In instantaneous torque, it's there. I have run it long term for heating tests. I had a party that said, oh, if you put the power into that seal, see, it's sealed, airtight, no dust, no magnetic filings, nothing can get in there. And I didn't have the shroud on it, and I didn't have a fan on it. I run it without any cooling, with 2100 watts going in for 4 hours, and it was still cold. It does not heat. But it looks nice with the cover on there, and it keeps something from bumping my Hall effect switches on the back that control this. In the finished product, it would be built a little bit neater than that. As I say, this is a first-time prototype. I have the designs over here for a 50 and 100 horse motor that will be 13 inches in diameter and 5 inches thick on a 50. On a 100 horse, it'll be 10 inches thick and still 13 inches in diameter. Here's a picture of the stator. You'll notice there's a very small amount of iron. I keep the iron to a minimum because two reasons. I've done extensive research on the saturation time of iron and how fast it will give me back the energy that I pushed into it. So the less iron I can use and still have the iron, to get high torque you have to have some iron. An ironless motor. I've got ironless motors at home, have no iron at all. They run beautifully, they're very efficient, and but they're not a high torque motor. They're like third horse, quarter horse, and they will work very nicely at that rate. But if I tried to go to a car motor, I have to have some iron to get the torque. And to increase the speed, I reduce the iron to the minimum so that I don't waste energy. Anytime that you're going to shove energy into a piece of iron and you have to put more energy in it than is necessary, you're wasting something. And the other thing that I looked at in working in the Navy with submarines and all the different types of electronics, some of it was secret at the time. Anytime that you can take X number of watts and make it do two jobs for you at the same time, getting from point A to point Z, and it does two jobs on its way there, you're coming out ahead. But if it only you take so much and do one job, and then you take so much more and do another job, when you can make the same supposed electrons do double work at the same time. So that's why I tried to make as efficient as possible